Okay, this video is for AP Calculus, and this covers what we call the Start Plus AccuMulation method. It's related to the Fundamental Theorem of Calculus, and this particular topic always appears a minimum of 2, sometimes 3 or 4 times on every AP exam, so it's really important. Plus, we're going to talk about something called displacement versus total distance traveled. All right, so when we first considered the Fundamental Theorem of Calculus, we were using the example of a car driving at a constant velocity, and we determined that the area under the function curve represented the cumulative distance traveled from that time t equals 0 to that time when we stop driving. Right? If we leave the ending value as a variable, then that means that we can produce a function of time. Right? So if you just say that you take the integral of the velocity variable, the area under the curve from 0 to 1, you're taking the antiderivative of velocity and plugging a 1 in, and the antiderivative at 0, and that's really the distance at 0 minus the distance you started. So that's a number. It represents the number of miles traveled. In this case, it would be, say, 60 miles, something like that. If you drive for 2 hours at 60 miles an hour, right, 60 times 2 is 120 miles. That's being accumulated here. And that's the antiderivative of the velocity with 2 plugged in minus the antiderivative of 0, which is the distance you are at the end minus the distance that you started, which is the number accumulated. So that's a number that would produce a value of accumulated miles. But if we leave this open and as a variable, then we get the velocity, the antiderivative of the velocity, which is the distance function at the location x, minus the location at the start. That gives me a function which allows me to vary x and determine the amount of miles accumulated up to that point whenever we stop. And we don't have to start at 0. We can start at a constant value and go, and that gives me the amount that's accumulated from that starting time to this variable time. Okay? So this produces functions which are called accumulation functions. Right, so the resulting function, we can call that an accumulation function. Now, although we've shown that this is true for a constant velocity, that's intuitive, that proof that we showed in the first half video, or the last section video, shows that this is true for any function. Conceptually, it means that if you have a function that represents the derivative of a quantity, how it's changing, for example, over time, then integrating that function from a constant to x will give a function for how that quantity that is the derivative of accumulates. We can use this fact to solve problems where we're given the quantity at a known time and given the rate of change of that quantity, its derivative, and then we're asked to find the quantity at a second time. I know this is confusing when I'm explaining it with words, but when we go through some examples, it'll make more sense. Okay, here's what it's based on. The way I kind of remember this idea is like this. Okay, we know the Fundamental Theorem of Calculus says if you have a derivative from a to b of f of x, the fundamental theorem says we can take the antiderivative of that function, take 2 copies of it, and plug in the b here and the a here. Okay? But what that means is if this function isn't the function, if this function is a derivative of it, so let's call it f prime of x, then the antiderivative would just be the underlying function. In other words, this is the derivative of this. So if this is f of x, the derivative would be f prime of x. This would be dfa, right? That means that if this is the derivative of a quantity, and you take an integral of that from some start to ending value, and this is going to give you the difference in that quantity, the quantity at b minus the quantity at a. It's going to give you the accumulation of that quantity. Okay? And then what we could do is solve for this. We could say, all right, let's say we have this function here. If we have the integral of f prime, we have a derivative function, and we have an a and a b here, and we say the antiderivative of that is f, and the antiderivative is f, and you plug in a b and an a, you could solve this for fb just by adding a to the other side. And that means fb would be fa, and then plus a to b integral of f prime of dx. Okay? So it's just an algebraic manipulation of the basic idea of the fundamental theorem of calculus. Okay, this is written a little more nicely. Let's say that t is time, And we wanted to find a function value at some ending time from some given function value that you know at the start. And that means you can take the start amount of the quantity, start amount, and you can add what's called the accumulation, which is the integral of the derivative of that quantity from the starting to the ending time, and that will equal the amount at the end of that time. So we call this method the SPAN method, start plus accumulation, or SPAN. Right? So we will use that idea to solve a number of problems here, so you can kind of see how it works. Let's say that we have a liquid flowing into a storage tank at a rate of this, liters per minute. If there are 40 liters of liquid in the tank at time t equals 2 minutes, how much liquid is in the tank at time t equals 10 minutes? All right. So what we have here is, let's make an expression for L. This is the rate of change of L, which means we're given L prime as a function of time. This is the rate of change of L. It is 180 plus 3t. Okay? And I also know that L at time 2 is equal to 40 liters. We're being asked to find the amount of liquid at time 10. So I have a starting amount, I have a rate of change of that quantity as a derivative, and I want to find an ending amount. So the start plus accumulation method says to find L at the end at time t is 10, we're going to take the amount at time 2, and we're going to get the accumulation by integrating from the start time to the end time of L prime of t. Okay, and I'm just going to use a calculator for a lot of these. So let me enter that function in here. It's 180. You could, of course, integrate this by hand, but I just want to do this quickly. So I'm going to say the integral, so I'm going to use math 9 and do the integral from 2 to 10 of that function, which I added into y1. So I will get that under variables, y variables. It's a function variable y1, and the variable q is used. So that's this number here. This is 1584. So that means that the amount of liquid at time 10 is equal to the amount of the liquid at time 2, which was 40 liters, plus this accumulation of, what was that number again? 1584. 1584. So if I add 40 to this number, that gives me the amount at the end, 1624. And the units there are liters. Start plus accumulation, which is an integral of the derivative of that quantity, equals the ending value. Okay, let's look at a few more examples. A hot air balloon. The height above the ground is changing at a rate given by this. The derivative of height is this, where h is in feet and t is in hours. If the hot air balloon is on the ground at time t equals 0, what is the height of the balloon at t equals 2 hours? All right, so what do we have? We have h of prime of t. We know that h at time 0 is, well, it's on the ground, so that means that the height is 0, and we're trying to find h of 2. That's the goal. Okay, so the setup for that is h of 2 is equal to the height at the start plus the accumulation from 0 to 2 of the derivative. Okay, and that means that since we're on the ground, we're just taking the derivative here. We can use, again, a calculator, or we can do it by hand. Let's do this by hand this time. 0 to 2 of negative 110t plus 550. So this would be h of 2 at 2, 0 plus. The antiderivative here would be negative 110. We're going to go up to 2 here and divide by 2, and then take this 550 and multiply by t and plug in a 0 and a 2. So that means this would be negative 110 over 2 with 2 plugged in, plus 550 with 2 plugged in. Now we would subtract the copy with 0 plugged in. 550 with 0 plugged in. 0 plus that gives me the height at 2. You can leave it in this form, but we do have to put what the units are. The height would be in feet. So if I didn't have a calculator, I would have answers that look like this. Okay, let's look at another example. There are 700 people in line for a popular amusement park ride when the ride begins operation in the morning. Once it begins operation, the ride accepts passengers until the park closes 8 hours later. While there is a line, people move onto the ride at a rate of 800 people per hour. The graph here shows the rate R of t at which people arrive at the ride throughout the day. The time t is measured in hours from the time the ride begins operation. How many people are in line for the ride at t equals 3 hours. All right. So first, I think we have to come up with a function for p. Let's make p be the function for the number of people. Yeah, maybe I could say we can deal with the rate. So this is going to be a function that is equal to the number of people in a line. Okay? That means the derivative of that is how fast people are moving into or out of the line. And it says that while there's a line, people move onto the ride they move onto the ride at a rate of 800 people. That means that they're exiting the line because they're going on the ride. But this graph shows the rate at which people arrive at the ride. So make sure that we can read that. Okay, so if we define p to be our function for the number of people, then the rate of change of p, which we could write as p prime, is going to be r of t, because that's how many people are arriving into the line to get on the ride, minus 800 people per hour are leaving the line to go on the ride. So if I take the number of people coming into line and the number of people leaving the line, this is how fast people are accumulating in the line, so how the rate of changes is riding. So if more people are arriving, like in this time frame where we have 1,000 people arriving and 800 are getting onto the ride, then more and more people are arriving, are adding to the line. The line's getting bigger. And once we drop below 800 here, right, that means that there's like, say, 600 people arriving, but 800 people are getting on the ride, so the number of people in line is decreasing. Right, so the line amount is going to grow or change according to this. It's going to grow whenever this is above 800, and it's going to shrink whenever this is lower than 800. But what we need to do is they're just asking for the amount of people at 3 hours. So I'm going to use my start plus accumulation. The amount of people at time 3 is equal to the amount of people at time 0 plus start plus the accumulation from 0 to 3 of that p prime of t. All right, so p at 3 would be the amount at 0, and it said when the ride begins operation, there are already 700 people in line, so that would be 700 people, right, plus this math 9. I'm going to use math 9 for this. They gave me r of t, so what I'm going to do is in my calculator, I'm going to enter this right here, this r of t. So r of t, oh, I guess I can't do it with a calculator because I'm going to need to find the area under a curve. All right. Yep, they didn't give me that directly. So I think I'm going to have to do something really quick. Well, let's write this out. I'll do another step here. This is p of 0 plus integral from 0 to 3, but this p prime of t is r of t minus 800. So I'm going to have to split this integral up. I'm going to do an integral from 0 to 3 of r of t, and then I'm going to subtract that same integral, a separate integral for the negative 800 here. Okay, so here, p of 3 is equal to the 700. For this, I'm going to have to evaluate this using the area under the curve, right? I can evaluate this if I have a graph of r of t, which I do. This is a graph of r of t. So between 0 and 3, I can evaluate this with area. So what I could do is maybe this. I could say this chunk here is an area which is, let's see, 800 times 3. 8 times 3 is 24, so that's 2400. This is a triangle area here, Let's do this. There's a rectangle here which is 200 tall and 2 wide, so that's going to be 400. And then there is a rectangle here which is half of this rectangle. This is, let's see, 200 times 2, that would be 400, but half of that is 200. And this is also 200 here. So it looks like I could evaluate this by adding area under the curve here for all that. So it's 2400 plus 400 plus 200 plus 200. And then for this integral, I don't have to use a graph. I'm just going to integrate this by hand to say the antiderivative is 800t, evaluated from 0 to 3, which means that's going to be 800 with 3 plugged in minus 800 with 0 plugged in. All right, so let's add that all up. That is 700 plus 2400 plus 400 plus 200 plus 200, and then minus this whole quantity, which is 800 times 3. Let's see, my notes say 1900, but my calculator right now says 1500. So let me see what the discrepancy is there. So it's in the area calculated here. So this is 800 times 3. Just want to make sure this is right. That is 2400. And this would be, let's see, 200 times 200 times 2. That would be 400. This is that same rectangle but cut in half and also in half again. So that'd be 4, 4, and 400. Yes, this is correct. So the answer here is 1,500 people. Okay, so a lot going on there. We're evaluating the integral in different ways. Area under the curve for part of it, by hand integration for the rest, with the fundamental theorem, the antiderivative. And then we're just adding that accumulation onto the 700 people that were there at the beginning. Okay, so that's the main topic, I would say, for today. But there's one other topic that we want to put in here, and there's just one example to show it. But it is important for physics problems. We're going to define the difference between displacement and total distance traveled. So displacement is, let's say that at one time you're at this location, and then you really have a positive velocity, so you move for a while like that. And then at time B, we have a velocity of 0, and then the velocity becomes negative, so we move back here and we end up here. Right? If you allow this positive and the negative velocity to cancel each other out somewhat, then that will give you a number here that represents the total distance from the ending position to the starting position. Right? And that is what we would get if we just evaluate the definite integral. Right? In other words, if I took a velocity function and I integrated it from time A to B, and I just directly integrated it like that, I'm going to get what's called displacement. Because that would mean that if I had an area where there was negative, that negative area would cancel some of the positive area, and you would get an overall smaller area. Sometimes we want that. That's called displacement. Sometimes we actually want to know the total path and distance traveled, which means we want to be cognizant of when we're adding to the total and subtracting from the total. So then what you want to do is one of two things. You can think of it as split this apart at some time here, like, well, I guess I wrote this as C, so I'll write this as C here. So let me back up. Right, so if I take the integral from A to C of the velocity, as is, I'm going to get displacement, because negative velocity is going to subtract some distance from positive. If I take the integral from A to C of v of t, and I'm cognizant of the fact that sometimes this is positive and sometimes that's negative, and I split this, so I have the positive part from A to B separated from the negative part from B to C, then what you can do is you can take this number, which would be negative, and multiply it by a -1 to force it to be positive, so that it adds to the total distance and you get the entire path length. That is called total distance traveled, which is different than displacement. Okay, another way to think of that is that you want the velocity to always be positive, so that if it is negative, you want it to act as if it was in the positive direction. Like you can effectively say, don't go backwards, take that same distance and go in this direction. So you could still do the integral from A to C or the velocity, but you'd have to take the absolute value of that to force it to always be positive. That's another way to get total distance traveled. Okay, so let's take a look at a couple ways that we can do this with this one. This is the last example for the notes here today. Okay, so a velocity function is given here, defined for t equals 1 to 5. For that interval, find the displacement over the interval and the total distance traveled. Okay, for the displacement, we're simply going to say the displacement is equal to the integral from 1 to 5 of the velocity. Okay, so if I were to do this in a calculator, I could put that function in here, variable squared minus variable minus 12. And then I could just use math 9 to integrate that from 1 to 5, integrating the y variable y1 with the variable p, and that gives me negative 18.667. The fact that that's negative means that if this is the positive direction, at t equals 1, we were here. We went, maybe the whole thing is negative, or it might have been positive for a while. Actually, it looks like it started negative, right? Probably what happened is at t equals 0, this started in the negative direction. At a certain point, this would become large enough that it would start to go in the other direction, but we never got far enough back to have an overall positive distance. We ended up 18.66 feet, I guess in this case, and we should put feet on there, from where we started. So that's called displacement. What is the distance away from the start that we ended up? Okay, for the other one, total distance traveled, there's two ways we could do this. We're going to have to be cognizant of where the function velocity is positive and negative. So let's graph that function in our calculator. We'll graph from 1 to 5. And then let's graph it. So it looks like this, get started in lower than that. So let's go from negative 20. Graph. Okay, so this starts at a negative velocity, and at a certain time here, it crosses over and becomes a positive velocity, which means just like what we graphed here. It goes negative for a while, there's a point where it comes to rest, and then it goes back in the positive direction. It doesn't get all the way back here because the displacement never gets to the positive side. What we could do is we could split this and find where that is by using the zero function. Where is this curve, this velocity 0? When does the particle come to rest and change directions? And that happens at t is 4. So what we can say is that this total distance traveled is going to be the integral from 0 up to 4 of the velocity. And then we're going to add on the negative. So I'm going to take a -1 times the rest of the integral. I'm sorry, actually it should be the other way around. We started with a negative velocity. So we're going to start with the negative of the 0 to 4, that integral, and then we're going to add the rest of the way from 4 to 6 because that is positive. So we're going to split this integral up at 4. So let's just do those as two separate integrals. If I've got that same function there, if I go from math 9 from 0 to 4, this is the period of time when it's moving in the negative direction. And I do that for everyone. That gives me negative 34.667. So this is negative 34.667, but we're negating that to force that to be a positive distance. And then we're going to add onto that the rest of the way to the same integral, but from 4 to 6. So if I go from 4 to 6, that's moving in the positive direction, so that will give me positive 16.667. So if I take the wrong button again there, if I take the negative of this first answer, and then I add it to this answer, I get the total distance traveled, which is did I not plug that in right? I'm not getting the answers that I've got on the answer key. Oh, this is right. Okay. I'm getting the answer 51.333. Okay, we're going to check this by doing it another way. I believe we can force our calculator to just do math 9 from 0 to, oh, I did from 0 to 6, that's why. Sorry. All right, trying to do too many of these videos in the same day, making too many mistakes. We have to start at 1, not at 0. So we're going to do the negative of the integral from 1 to 4 of the velocity, and then we will add the rest of the way from 4 to only to 5. Okay, we're only integrating from 1 to 5, so we're splitting it at 4, but we're not going from 0 to 6. For some reason I have 0 and 6 in there. So let's do that again. We'll take the same function, but we're taking from 1 to 4. This is the negative part. That gives me negative 22.5. So negative of negative 22.5 plus positive is just the integral from 4 to 5. So an integral, same velocity function, but from 4 to 5. And that gives me 3.833. So if I were to take this number and subtract this negative number to make a positive distance, we will get 26.333. That does much more. Again, this is an accumulated distance, so that would be feet. The other way to do this is to say that this is equal to just from 1 to 5, the absolute value of the velocity function. Just force it to be always positive and just integrate it once. You can do that actually. We're just going to go math 9, the whole integral from 1 to 5. But there is, under the math menu, if you scroll over to the numbers, there's an absolute value function. And then we can insert the velocity function from y1. And integrate that. That should give me, in a single integral, the same value, 26.333. So that's another way that you can do that. You can just show that as the work, 26.333, and then the units feet. Okay, that should be the last of the examples. Okay, that's going to wrap up the first half of this unit. We always teach this in 2 parts, so we'll have a separate test over this part. The second half of Unit 4 is going to be about integration techniques, so things that go beyond just using the antiderivative shortcuts. This first section covered a whole bunch of applications and things related to that.